Okay, hello, thank you for the introduction. And I will talk about a new tool for meta-analysis, which we call NeuroQuery. So the general goal is brain mapping. It's to associate mental functions and pathologies and anatomical terms with structures and positions in the brain. And we try to look for this mapping information in the existing neuroimaging literature. This is an approach called meta-analysis, and NeuroQuery is a new tool for performing meta-analysis. And unlike existing approaches, it can encode full documents and not only single terms into brain maps. And also, it can produce meaningful brain maps for a very large vocabulary, including rare terms which occur in few studies and which are out of reach for traditional meta-analysis. So, very briefly, the idea behind meta-analysis is to gather many neuroimaging studies and try to find where their findings agree. Because there's a huge literature of neuroimaging, so it can be overwhelming, and it's good to have statistical summaries. And also because some systems are studied almost in isolation, whereas we want a comprehensive model of the brain. And sometimes findings can be specific to a particular experimental setup or a certain group of subjects. So the goal of meta-analysis is really to gather as many studies as possible and discover effects that are reported consistently across studies. And the way it's usually done is that you start from a concept like calculation, gather many studies that reference this concept, and aggregate their peak coordinates, smooth and threshold the resulting map. And this can be automated and done at a very large scale with a fantastic tool that many of us use, which is called NeuroSynth. And it works with dozens of thousands of studies and allows you to very easily test the independence between the activity of each brain voxel and the occurrence of a particular term in the corresponding study. And this works very well in most cases, but it still has the limitation of all the existing meta-analytic tools, that it treats each word independently of the other concepts. So for a particular term, it splits the literature into studies that reference this term and studies that don't, and compares the peak activations for these two groups. But it doesn't look at the other terms that occur in the studies. And as a result, first of all, it has no natural mechanism to combine terms. So if you're interested in a concept that cannot be easily described with a single term, it cannot provide a result. And for rare terms which occur in very few studies, it lacks statistical power because peak activation coordinates are a weak signal, and you need many examples in order to detect a pattern in these peak activation coordinates. On the other hand, it's much easier to see that some words actually often co-occur and are related to each other. So maybe if, for example, aphasia occurs in very few studies, it will be hard to find a pattern in their peak activation coordinates. But even with very few examples, it's quite easy to see that it always appears in studies together with language or terms related to language. So the idea behind NeuroQuery is to rely on this information and on the relationships between words in order to be able to encode full documents and also recover brain maps for terms that occur in few studies by relying on other related terms that are easier to encode. There's also another, we could also use images rather than peak activation coordinates for meta-analysis, but unlike images, peak activation coordinates are available for thousands of studies, which is why many meta-analytic tools focus on meta-analysis of peak activation coordinates. Now, there is one existing tool that tries to combine words and use this information from their relationships, called Generalized Correspondent Latent Dirichlet Allocation. It's an adaptation of the LDA topic model used in natural language processing. and it models each study as a mixture of topics, of latent variables, and each topic is associated with a distribution over the term in GCLDA's, the vocabulary that GCLDA uses, and a mixture of Gaussians in the brain. But it's much too slow to be used in production in a website like NeuroSynth. And also, as you can see, the mixture of Gaussian model results in low spatial resolution. So for NeuroQuery, we have taken a completely different approach. And instead of trying to build a generative model of the joint distribution of text and peak activation coordinates, we have decided to treat this as a supervised learning problem and trained linear regression models to predict the density of peak activations given the text of a study. So for each study in a corpus of 14,000, the text is extracted and is represented by a vector of term frequencies where each coordinate corresponds to the number of occurrences of a term from a very large vocabulary in the text of this study. And then the activation across all studies of each voxel in the brain is regressed on these term frequency descriptors of documents. And since we use a very large vocabulary, not all words have the same importance, and some are noisy. So we use a feature selection procedure that automatically identifies a small set of terms that have a very strong link with brain activity. And it also adapts the regularization that is used for each of these features. And when we have to map a query into brain space, it is first mapped onto this small, well-encoded vocabulary, and then translated into a brain map through the linear regression coefficients. So in order to do this, we use a semantic similarity matrix. It's a matrix of associations between words, which is derived from co-occurrence statistics in the literature. And when we get a query, we expand it or we smooth it by putting some weight on all the terms that are related to it and that co-occur a lot with it in the literature. And then this is projected on the small vocabulary that has a very strong link with brain activity, and the resulting representation is mapped into brain space through the linear regression coefficients. And this tool is already online, so feel free to go to the website and try it out. And the website shows you exactly this. You enter text, which can be any query. It doesn't need to be a single word. You could copy-paste an abstract in there. And then you will get a list of related terms, and finally the resulting brain maps. And below you can also see a list of related documents that you can find on PubMed. And this gives reasonable maps for many terms that are challenging to traditional meta-analysis methods, either typically because they are too rare and traditional methods lack statistical power. So here are a few examples. And in order to verify this better encoding of rare words, we have performed ablation studies where we made words artificially rare by deleting them from many documents. So for example, for language, starting from a full corpus where it occurs in thousands of documents, we randomly erase it from many studies until it occurs in only 100 studies and even in only 16 studies. And we see that even with very few examples, NeuroQuery still gets a reasonable map that looks a lot like the map it gets for the full corpus or the map that NeuroSynth provides when trained with a full corpus, whereas other methods very quickly start to lack statistical power and report very few activations. And we have averaged this across several words, and we see that quantitatively, NeuroQuery does cope much better with terms that occur in very few studies. Another interesting aspect of NeuroQuery is that it's a predictive model. It's not just an in-sample summary statistic, but it can generate predictions for out-of-sample documents. So in order to see this, we have performed cross-validation, where we set aside a test set when training the model, and then for each left-out document in the test set, We give it to the tool, it predicts a density, and we look at the likelihood of the coordinates which were actually reported in the predicted density. And we see that NeuroQuery performs well for this task. GCLDA also performs well, but suffers from its lack of spatial resolution. And we can see that NeuroSynth doesn't have a mechanism to combine words, so it simply isn't designed to perform this kind of task. So to summarize, I've presented NeuroQuery, which is a new tool for encoding arbitrary text into brain maps. It's a new meta-analysis method, and unlike previous approaches, it can encode full documents, not only single predefined expressions, and it works with a much larger vocabulary. So now users don't have to adapt their questions to the restricted vocabulary that the tool understands, and NeuroQuery automatically maps users' questions to vocabulary that has a strong link with brain activity, and uses this to map it and provide meaningful brain maps. And I would like to thank the other people who participated in this work, and thank you for your attention.